Here we're asked to graph polynomial p of x equals x cubed minus 2x squared minus 4x plus 8. First, we're going to check the symmetries. So let's just say symmetries here. And you'll note first that this is not a quadratic function. It's not second degree, so we know we're not going to be able to use the axis of symmetry x equals minus ba. The only thing we're going to be able to do is check the p of negative x and see what we got. So p of negative x, the quick way to do this is to take every odd power and change the sign in front of it, because that would be the result if we inserted a negative x in parentheses for each of the x's. So this becomes a negative x cubed, and this is x to the second, so the sign doesn't change. It remains negative x 2x squared. X to the first is negative, is odd, so we're going to change the sign to positive 4x to the first, and then plus 8 never changes. Well, clearly that's not p of x, so we don't have p of negative x equals p of x. The best we might try for is to factor out a negative sign and see if this is negative p of x. That would leave x cubed, positive 2x squared, minus 4x, minus 8. No, that's not. That result there is not negative p of x. So there are no symmetries in this. No symmetries. We don't have to worry about that anymore. We checked. There are none. Next thing we're going to do is figure out the location of the x-intercepts and the behavior of the function at those intercepts. So we take the original p of x and we factor it. It has 4 terms, so we're going to factor by grouping. I'll let you do the details. I'll put the results here. We have x minus 2 times x plus 2 times x minus 2. Regrouping that so we can write it in exponential form, we have x plus 2 to the first power times x minus 2 to the second power. The zero product property, if we set y, in other words p of x equal to 0, to find the x-intercept, the zero product property said we set each of the factors equal to 0 and solve x plus 2 to the first will end up giving us the root, or the 0, x equals negative 2, while the x minus 2 to the second, set that equal to 0 and solve, and we're going to end up with x equal positive 2 when we solve. Okay, so x equal negative 2, that implies that we're going to have an x-intercept located at the ordered pair negative 2 for the x-coordinate, 0 for the y. And because we had an odd multiplicity, and that was determined by the power on the factor, it was odd, that implied that this x-intercept is going to be a cross. In other words, we're going to cross the x-axis on the graph at this ordered pair. This other one, x equals 2, it had a multiplicity of 2. So it gave us an x-intercept at the ordered pair 2, 0, and it was even because, like I said, the power on the factor that contains this root is 2. It's even, so it has an even multiplicity, and that implies that the function, the graph of the function, is going to kiss the x-axis at the x-intercept instead of crossing. Okay, next thing we're going to do is build a sine graph, and that's going to talk about the position of the function in certain intervals of x values. Sine graph. Okay, so I'm going to have an x-axis here. I'm going to partition it in a moment using the x-intercepts here at negative 2 and here at positive 2. So draw a dotted line, draw a dotted line. Now, we're anticipating that the graph is going to cross at negative 2, but it's only going to kiss at positive 2. So let's figure out the sign of the function in each of the regions. P of x is equal to factored form, x plus 2 to the first times x minus 2 to the second. So what we know is that the second factor will always be positive because we are raising it to the second power. It doesn't matter what x you choose, second factor will always be positive, so we'll record that. Now we'll check and see what the sign is on the first factor, x plus 2, for values we choose in each of the regions. Let's choose values of x to the left of negative 2. Say, for instance, test any point to the left. I'd say x equal negative 100. When x is negative 100, the factor x plus 2 is negative 100 plus 2, it's negative. And then we get a negative times a positive, which gives us a negative result. In the middle, let's choose a value of x between negative 2 and 2. Let's say 0. Then get the sign on the factor x plus 2. 0 plus 2 is positive. Positive times a positive means we're going to get positive y values for x's, or positive values for the function, in other words, when the x values are between negative 2 and 2. And then to the right of 2, let's choose a test point x equal positive 100. Plug it into the first factor, x plus 2. And that's going to give us positive. A positive times a positive is positive. Oh, it didn't even change signs. And you know what? That is cool with us because we already know this function crosses or touches at the intercepts that we have here. And at negative 2 on the x-axis, it's a cross because of the odd multiplicity of the factor. So it's going it's going to change from negative on the left of negative 2 to positive on the right of negative 2. So what is it that's changing? This guy right here, he's p of x. He's the y values of the function. So that means we're going negative, negative, and then we're going positive because we're crossing here. The other one's a kiss. We know that because of the even multiplicity of this x-intercept. So if it's going to be positive between negative 2 and 2, the y-coordinates, then they're going to remain positive afterwards. So this thing's going to somehow turn around, come back around, and kiss and go back up. And the graph will look something like that. Now, we can actually be more accurate by choosing a value. Let's choose a value between negative 2 and 2. That would be revealing to us. So we're going to choose, well, it doesn't have to just be 1 point. We'll choose a few points, and it will give us accuracy in our graph. So we'll make a little table, x, y's. All right, the first one that I'm really curious about is what happens at x equals 0. This will be the y-intercept. That's 0 for the x-coordinate, and the y-coordinate, if you plug it in and simplify it, will be 8. And then just a couple more points. Let's see that when x is equal to negative 1, plug it in. You'll simplify and get 9. And when x is equal to positive 1, you simplify and get 3. Oh, that's enough. That's more than enough. I think just the y-intercept would probably be sufficient. Okay, so put this all together and do our rough graph. And we have, let's see, we're down here, and we're going to go as far up as the y-intercept at 8. And then when we're at negative 1, we're going to be all the way up to 9. And then we're crossing at negative 2. And we're also kissing at positive 2. So the graph looks something like this. You know it's negative before we get to, we're on the left side of negative 2. It's down here. Then we come up. We have our ordered pair, negative 1, 9. And we're going to come back around. We have our y-intercept at 0, 8. Then we're going to come down and kiss the axis and turn around and come back up. Now you see we didn't even discuss the end behavior. Let's make sure that that's all cool. Well, let's do it without even writing anything down. Did we expect it to be dipping to the left? Well, it was an odd degree, so we knew it was going to be one side would be down, and the other side would be up, or the one side would be up, the other side would be down. The lead coefficient was positive 1 times x cubed, so we did expect it to be downward on the left side and upward on the right side. We could have done that extra test, but it turns out that we saw that when we did the sine graph, so we really didn't need to do more than that. And we are finished.